What is nuclear engineering? At its core, nuclear engineering is about controlling the energy of the atom. When we talk about nuclear energy, we're referring to the nuclear binding energy that holds the protons and neutrons of an atom's nucleus together. By either splitting heavy atomic nuclei or fusing light nuclei together, we can release huge amounts of energy. The energy density is astounding. For example, fissioning just 1 gram of uranium fuel can yield as much energy as burning 3 tons of coal, and it does so without emitting carbon dioxide. Nuclear engineering is the discipline of applying this powerful science in practical, safe, and innovative ways. Nuclear fission, the splitting of a heavy nucleus, is the principle behind today's nuclear power plants. Discovered in 1938, fission was first harnessed in the early 1940s as scientists built the first controlled nuclear reactor amid efforts to develop atomic weapons. After World War II, the focus broadened to peaceful uses of the atom, leading to the first electricity-producing reactor in 1951 and the first commercial nuclear power stations by the mid-1950s. In a fission reactor, engineers arrange fuel in a configuration that sustains a chain reaction. A neutron splits a uranium atom, releasing energy and more neutrons that go on to split other atoms. By using control rods that absorb neutrons and moderators, like water, that slow neutrons down, engineers can control the reaction rate to keep it steady and safe. The heat from fission is used to boil water into steam and drive turbines, just like in a coal plant, except the heat comes from breaking atomic bonds instead of burning fossil fuel. The result is carbon-free electricity on a large scale. A typical nuclear reactor unit produces on the order of 1,000 megawatts of electric power continuously, enough for a city, using fuel that only needs refueling every 1 to 2 years. Nuclear fusion, the fusing of light nuclei, like hydrogen isotopes, into heavier ones, is the process that powers the sun and stars. It promises an even more abundant source of energy, with no long-lived radioactive waste and no risk of meltdowns, but it's also much harder to achieve on Earth. Fusion requires extreme temperatures to overcome the repulsive forces between nuclei. While no fusion power plant exists yet, nuclear engineers and physicists are actively working on it. The flagship project is ITER in France, a huge international collaboration to build the world's largest experimental fusion reactor. ITER's goal is to produce 500 megawatts of fusion power output from 50 megawatts of input heating, essentially getting 10 times more energy out than put in, albeit for short bursts. 33 nations are involved in ITER, constructing a device that will use powerful magnets to confine a superhot plasma of hydrogen isotopes. ITER won't generate electricity, but it aims to prove the feasibility of fusion as a large-scale energy source. Originally, ITER hoped to achieve a first plasma by 2025, but due to engineering challenges, the schedule has been pushed back. The latest plans anticipate initial fusion operations, with deuterium fuel, around 2035, followed by full-power deuterium-tritium reactions later in the 2030s. Even though it's taking time, the very fact that engineers are assembling such a complex machine, a star in a bottle, underscores how ambitious and forward-looking nuclear engineering can be. Powering the world, reactors and innovations. When most people think of nuclear engineering, they picture the large concrete domes of nuclear power plants or maybe the iconic silhouette of cooling towers on the horizon. Indeed, nuclear power generation is a central pillar of nuclear engineering. Today's commercial reactors are mostly light water reactors, which means they use ordinary water as both coolant and neutron moderator. These include pressurized water reactors and boiling water reactors, technologies developed in the mid-20th century that have been refined over generations. Engineers categorize reactors by generation. Generation I were the early prototypes in the 1950s and 1960s. Generation II are the workhorses, like the big reactors built in the 1970s and 1980s still running today. Generation III are more advanced designs with enhanced safety, and Generation IV refers to innovative future reactors currently in development. Nuclear engineers have continuously improved reactor safety and efficiency. For example, modern reactors have multiple backup cooling systems and robust containment structures to prevent radiation release. And contrary to the dramatic images from movies, reactors cannot explode like nuclear bombs. The fuel is not enriched nearly enough for that, and the physics are completely different. The focus for engineers is on safe, controlled heat generation. One exciting area in power reactor innovation is the development of small modular reactors, SMRs. SMRs are defined as nuclear reactors producing up to about 300 megawatts per unit, designed to be built in factories as modules. Instead of one giant reactor built on site over many years, an SMR plant could have a set of small reactors assembled from prefabricated components. This approach promises shorter construction times and lower upfront costs, which could make nuclear more accessible and flexible. For instance, NuScale Power, a US company, has developed an SMR design where each module produces about 77 megawatts. A single plant could contain up to 12 modules for a total of 900 megawatts, but operators can install modules one by one as needed. In 2023, NuScale's design became the first SMR design certified by the US Nuclear Regulatory Commission, a major milestone in bringing this technology to market. NuScale's reactor modules are designed to be self-cooling and passively safe. They sit in a water-filled pool underground, and if there's any malfunction, the reactor will cool itself without needing external power or human intervention. The idea is that a small reactor can be deployed in remote regions or to replace old coal plants, providing steady, carbon-free power with a much smaller land footprint and capital investment than traditional reactors. Countries like the United States, Canada, and the UK are looking at SMRs as part of the future energy mix. Another groundbreaking concept moving toward reality is advanced Generation 4 reactors. These include designs like fast breeder reactors, high-temperature gas reactors, and molten salt reactors, many of which can achieve higher efficiency or consume nuclear waste as fuel. A prominent example is TerraPower's Natrium reactor, backed by Bill Gates' nuclear innovation company TerraPower. Natrium is a 345 megawatt sodium-cooled fast reactor with an integrated molten salt energy storage system. Instead of water, it uses liquid sodium metal as the coolant, which allows the reactor to operate at atmospheric pressure and very high temperature for improved efficiency. The molten salt storage acts like a built-in battery. The reactor can transfer heat to a salt tank, which can then release that heat to generate extra steam when electricity demand spikes. This means Natrium can boost its output to about 500 megawatts for short periods by drawing on stored heat, a flexibility that pairs well with renewable energy sources on the grid. It also boasts 3 times better fuel utilization than today's reactors and about 40% less nuclear waste per unit of energy produced. TerraPower, partnering with GE Hitachi, is building a demonstration Natrium plant in Wyoming, at the site of a retiring coal plant, with substantial support from the US Department of Energy. The project timeline aimed for operation by 2028, but a snag in obtaining fuel has pushed it a couple of years later. The Natrium reactor uses HALEU fuel, which is a new fuel form not yet produced at large commercial scale. When the primary supplier, in Russia, became unavailable, it caused a delay in the schedule. Still, TerraPower is pressing ahead with construction and licensing, and the Natrium demo should be online around 2030. If successful, it will showcase a new breed of nuclear technology that is safer, more flexible, and more efficient. In addition to fission innovations, nuclear engineers are also working on fusion prototypes beyond ITER. There are startup companies and national labs exploring alternative fusion approaches, from stellarators to compact tokamaks with high-temperature superconductors, all aiming to crack the fusion puzzle. The timeline for commercial fusion power remains uncertain, but progress in materials and plasma physics is steady. Many in the field are optimistic that by the middle of the 21st century, fusion will start to complement fission as a practical energy source. Whichever way we generate nuclear heat, splitting atoms or fusing them, the job of nuclear engineers is to make it reliable and safe. Safety is absolutely paramount. Engineers design reactors with multiple layers of protection, from robust containment domes to automatic shutdown systems, and strict operational protocols. The events of accidents like 3 Mile Island, Chernobyl, and Fukushima have only reinforced the safety culture and led to even better reactor designs and emergency preparedness. Modern reactors are built to withstand extreme scenarios, and advanced systems even passively shut down and self-cool without human intervention or external power. Beyond power, medicine, space, and more. While energy production is a huge part of nuclear engineering, it's far from the whole story. Nuclear technology quietly permeates many aspects of modern life in ways you might not realize. For example, if you or a loved one has had a diagnostic scan or a cancer treatment, nuclear engineering was likely at work behind the scenes. The field of nuclear medicine relies on radioactive isotopes to detect and fight disease. In a typical year, over 40 million nuclear medicine procedures are performed globally, from PET scans to targeted radiation therapies. One of the most common medical isotopes is technetium-99 m, used in millions of imaging scans annually to diagnose heart disease, cancer, and other conditions. This isotope is produced in nuclear reactors by irradiating molybdenum targets, a process that requires precise engineering and regulatory control to ensure purity and safety. Another example, cobalt-60, a radioactive form of cobalt produced in certain reactors, is a workhorse isotope with a variety of uses. It emits gamma rays that are harnessed to sterilize medical equipment. In fact, cobalt-60 irradiation sterilizes about 40% of the world's single-use medical devices like gloves, syringes, and surgical instruments. Cobalt-60 is also used in radiation therapy to treat cancer, and newer techniques like gamma knife radiosurgery rely on focused gamma rays, often from cobalt sources, to destroy tumors with millimeter precision. Nuclear engineers contribute to medicine not only by producing isotopes, but also by designing the reactors and facilities that make them, and by calculating safe radiation doses and shielding. Medical isotope production requires reactors like the University of Missouri Research Reactor, a university-run reactor that runs nearly 24/7 to supply isotopes for hospitals. Engineers ensure these reactors operate safely and that the precious isotopes are delivered on time. There's even exciting research using nuclear techniques for new cancer treatments. For instance, researchers are exploring isotopes like astatine-211 and thorium-229 for targeted alpha therapies that can seek out and destroy cancer cells with minimal damage to healthy tissue. In these cutting-edge projects, nuclear engineers work hand in hand with chemists, physicians, and biologists. It's a highly interdisciplinary effort. Another realm where nuclear engineering shines is space exploration. Space is a harsh environment that demands reliable power sources far from the sun. That's why many spacecraft use radioisotope power systems, commonly known as radioisotope thermoelectric generators, RTGs. RTGs contain a chunk of radioactive material that naturally emits heat as it decays. Thermoelectric devices then convert that heat into electricity. This technology has been providing power to spacecraft since the 1960s. Plutonium-238 is ideal because it has a long half-life, 88 years, and emits steady heat with minimal gamma radiation. RTGs have powered famous missions like Voyager 1 and 2, which have been sailing through space since 1977 and are still sending back data over 45 years later, thanks to their RTGs. The Curiosity and Perseverance rovers on Mars, the New Horizons probe to Pluto, and the Cassini spacecraft at Saturn all ran on RTGs as well. These generators are incredibly rugged. They can provide electricity and warmth for decades in the vacuum of space where solar panels alone wouldn't suffice, like on the dark side of planets or far from the sun. Nuclear engineers and scientists design these power systems and also solve challenges like shielding and safety. For instance, making sure that if a rocket explodes during launch, the nuclear material stays contained and doesn't harm anyone. Looking to the future, nuclear engineers are working on nuclear propulsion for spacecraft. NASA and DARPA have initiated the Draco program to demonstrate a nuclear thermal rocket engine in space by the late 2020s. A nuclear thermal rocket would use a compact fission reactor to superheat a propellant and shoot it out a nozzle to produce thrust. This could provide much higher efficiency than today's chemical rockets, potentially 2 to 5 times greater fuel efficiency, with thrust 10,000 times higher than electric ion engines. In practical terms, a nuclear-powered rocket could cut the travel time to Mars nearly in half, making crewed missions safer and more feasible. The Draco demo aims to test such an engine in Earth orbit. Nuclear engineers on this project must tackle unique issues, designing a reactor that is lightweight yet robust, figuring out how to start it only once in space and using high-assay low-enriched uranium fuel so that it doesn't require weapons-grade material. If successful, nuclear propulsion could open up deep space in ways that were once confined to science fiction. Back on Earth, nuclear techniques also find use in industry and research. For example, industrial radiography uses radiation to X-ray welds and structures to check for cracks, a vital method for quality control in construction and manufacturing. The process of food irradiation uses gamma rays to kill bacteria in foods, extending shelf life without making the food radioactive. Even archaeology and art benefit from nuclear tech. Methods like neutron activation analysis can determine the composition of ancient artifacts without damaging them, and carbon dating is fundamental for determining the age of fossils and historical objects. These examples barely scratch the surface, but they illustrate a key point. Nuclear engineering isn't just about keeping the lights on, it's also about saving lives, exploring new frontiers, and advancing knowledge. Life as a nuclear engineer, careers and pathways. With such a wide range of applications, what does it mean to be a nuclear engineer? What kinds of jobs exist, and how do you prepare for them? In a nutshell, nuclear engineers research, design, and manage systems that involve nuclear processes and radiation. Depending on their role, they might be designing a new reactor core, developing protocols for handling nuclear waste, running computer simulations of neutron behavior, or writing safety standards for radiation use. Let's break down a few major career areas in nuclear engineering. Power generation. Many nuclear engineers work at nuclear power plants or with companies that design reactors. They may monitor nuclear plant operations to ensure everything runs safely and efficiently. They develop and test procedures for managing nuclear fuel and disposing of waste. Some oversee the construction of new reactors or upgrades to existing ones, making sure all systems, like mechanical, electrical, nuclear, integrate properly. In a power utility, a nuclear engineer might start out analyzing reactor performance data and later advance to supervising reactor operators or managing technical teams. Safety and regulatory compliance are big parts of the job. Nuclear engineers must ensure their plant meets all Nuclear Regulatory Commission requirements and that any changes go through rigorous safety analysis. Defense and naval reactors. In the defense sector, nuclear engineers work on nuclear propulsion systems for naval vessels. They might design next-generation reactors that are more compact or efficient for ships or help maintain and refuel the existing fleet reactors. They also play a role in nuclear weapons stewardship, ensuring the safety and reliability of a country's nuclear arsenal without actual testing, through simulations and inspections. This is highly specialized and often involves working for government laboratories or defense contractors under strict security clearance. Naval reactor engineers may also serve at sea, for example, as reactor engineers on an aircraft carrier, responsible for monitoring the reactor and training the crew in nuclear operations. The military also trains many nuclear engineers. Some start their careers as nuclear officers in the Navy and then transition to civilian roles. Research and academia. Many nuclear engineers work at national laboratories, universities, or private R&D companies. Here, the job might involve developing new reactor technologies, materials, or computational methods. For instance, research nuclear engineers are pushing the envelope on fusion energy, advanced fission reactors, nuclear fuel recycling, and better radiation detectors. They also delve into fundamental questions, like studying what happens to reactor materials after years of neutron bombardment. Some nuclear engineers become professors, teaching the next generation and conducting research. An example research path could be working on improving models of reactor thermal hydraulics or on nuclear security topics such as nonproliferation, such as technologies to detect illicit nuclear material transport. The work is often collaborative. Nuclear engineers frequently team up with other specialists to solve complex problems. Medical and health physics. In healthcare, medical physicists design and maintain radiation therapy equipment, calculate safe doses for cancer treatments, and ensure imaging devices are properly calibrated. Nuclear engineers in this sphere might oversee the production of medical isotopes or manage a hospital's radiation safety program, making sure CT scanners, X-ray machines, and radioactive sources are used safely and meet regulations. There is also the field of health physics, which is all about radiation protection. Health physicists establish protocols to protect workers and the public from unnecessary radiation exposure, whether at nuclear plants, hospitals, or industrial sites. Space and remote applications. As discussed, nuclear engineers contribute to space missions by designing reactor and power systems for spacecraft. With new plans to establish bases on the Moon or Mars, there is ongoing work on small nuclear reactors for remote power. For example, NASA's Kilopower project recently tested a small reactor prototype that could provide electricity for a lunar or Martian habitat. Designing these systems involves skills at the intersection of nuclear engineering, thermal engineering, and aerospace. There are also terrestrial remote applications, such as microreactors that could provide power in remote communities or disaster areas. Startups and government labs are actively developing these, and they need nuclear engineers to solve challenges of miniaturization, automation, and licensing. Regulation and policy. Some nuclear engineers pursue careers with regulatory bodies or international agencies. In the US, the Nuclear Regulatory Commission employs many nuclear engineers as inspectors, license reviewers, and safety analysts. They review designs for new reactors, analyze operating plants' performance, and develop regulations to ensure public health and safety. Internationally, nuclear engineers work with organizations like the International Atomic Energy Agency on safeguarding nuclear materials and helping countries set up regulatory infrastructures. There are also policy-oriented roles. advising governments on nuclear energy strategy, waste management policy, or emergency preparedness. Each of these paths requires a solid foundation in nuclear science and technology, but the specific skill emphasis can vary. So, how do you become a nuclear engineer? Typically, you will need at least a bachelor's degree in nuclear engineering or a closely related field. In college, nuclear engineering students take courses in physics, advanced mathematics, and engineering fundamentals. Specialized courses cover topics like reactor theory, nuclear reactor design, radiation detection and measurement, health physics, and nuclear fuel cycle technology. Many programs also include labs where students might experiment with subcritical reactors or study radiation shielding in practice. Some universities have a research reactor on campus, giving students hands-on experience with operating a reactor under supervision. It's worth noting that nuclear engineering is multidisciplinary. You'll touch on electrical engineering, chemical engineering, materials engineering, and even data science. Therefore, successful nuclear engineers tend to have strong analytical and problem-solving skills, and they're able to integrate knowledge from different fields. Attention to detail is critical. When you're dealing with nuclear systems, safety depends on getting the details right. Communication skills are also important. Nuclear engineers often work in teams with other engineers, technicians, and scientists, so they must be able to explain complex concepts clearly and write clear technical documentation. Many nuclear engineers go on to earn graduate degrees, especially if they want to specialize in research, academia, or advanced design work. Higher degrees allow one to focus on subfields like fusion engineering, nuclear materials, or medical physics, and they can open doors to higher-level positions. However, a bachelor's degree can be sufficient for entry-level jobs in industry or government. Regarding professional licensing, in some countries like the United States, engineers can pursue a professional engineer (PE) license. For nuclear engineers, getting a PE license involves first passing the Fundamentals of Engineering exam, working under a licensed engineer for typically 4 years, and then passing the nuclear PE exam. While not all nuclear engineering roles require a PE license, it can be useful for career advancement. It signifies you can take legal responsibility for engineering projects and may be required if you work as an independent consultant or supervise certain projects. On the job, nuclear engineers often undergo continuous training. Regulations and technologies evolve, so staying current is part of the profession. For example, reactor engineers at a power plant must requalify on simulators regularly, and health physicists might need to refresh their certifications. Professional societies like the American Nuclear Society or the Nuclear Institute, in the UK, provide resources, conferences, and courses to help engineers keep learning throughout their careers. What about the job outlook? It can depend on the country and the energy policies in play. In the US, the Bureau of Labor Statistics projects a modest decline in the number of nuclear engineering jobs over the next decade, largely due to a slowdown in new reactor construction and a growing focus on renewable energy. However, it's important to realize that many current nuclear engineers are nearing retirement, so companies and agencies will be hiring to fill those gaps. About 700 openings per year in the US are projected, mostly to replace retiring workers. Globally, the picture can be quite different. Countries like China and India are expanding their nuclear fleet significantly, creating demand for thousands of new nuclear engineers. And the rise of advanced reactor startups and fusion companies is starting to invigorate the field with a more entrepreneurial spirit. In short, for young engineers with a passion for nuclear science, there are plenty of challenges to tackle and opportunities to pursue, especially if you are adaptable and willing to follow the demand. One rewarding aspect of a nuclear engineering career that veterans often cite is the sense of purpose. You could be part of providing clean energy to mitigate climate change, developing technology that saves lives in hospitals, or contributing to the exploration of space. There is also a strong community among nuclear professionals, a shared commitment to safety, curiosity about science, and an understanding of the responsibility that comes with working with powerful technologies. It's not a career to take lightly, but it's one that can have outsized impacts on society. The future, challenges and exciting possibilities. As we look to the future, nuclear engineering sits at the intersection of some of the 21st century's biggest challenges and opportunities. A major driver for renewed interest in nuclear technology is climate change. Nuclear power offers a source of baseload electricity with zero carbon emissions at the point of generation. With many countries setting ambitious targets for reducing greenhouse gases, there's a growing recognition that alongside wind, solar, and other renewables, nuclear may play a key role in a balanced, carbon-free energy grid. we are likely to see a more diverse set of reactors in coming decades, from large traditional plants to small modular plants, microreactors for remote areas, and demonstration fusion plants, if engineering goals are met. Nuclear engineers of the future will also be deeply involved in solving the nuclear waste puzzle. While the volume of waste from nuclear plants is small relative to the energy produced, it remains highly radioactive for long periods and must be managed with utmost care. Several technological and policy approaches are being pursued: deep geological repositories to safely isolate spent fuel deep underground for millennia, reprocessing and recycling of fuel to extract more energy and reduce the most long-lived isotopes, and even advanced transmutation reactors that could burn some components of waste. Turning these solutions into reality will require not just technical prowess but also public engagement and international cooperation, areas where nuclear engineers and scientists will need to collaborate with policymakers, communicators, and the public to build trust and consensus. Another growth area is nuclear engineering in the service of non-electric applications. For instance, using nuclear reactors to produce clean hydrogen fuel is being explored. A nuclear plant could provide the heat or electricity to generate hydrogen without carbon emissions, which could then be used for energy storage or in industries like steelmaking. There is also interest in desalination, using the heat from nuclear reactors to turn seawater into fresh water, which could alleviate water scarcity in arid regions. Already, some of the plans for SMRs involve cogeneration of electricity and heat for industrial uses. By broadening the mission of reactors beyond just electricity, nuclear engineers could help decarbonize multiple sectors of the economy. On the more visionary end, if projects like NASA's nuclear thermal rocket succeed, we might see nuclear-powered spacecraft enabling human missions to Mars and beyond in the not-too-distant future. Nuclear propulsion could make deep space exploration faster and more feasible, unlocking possibilities like rapid supply ships to Mars colonies or robotic probes reaching the outer planets in record time. And if fusion energy is eventually mastered, whether via ITER or one of the innovative private ventures, it could revolutionize how we power our world. Fusion, being effectively an inexhaustible energy source and inherently safe, has been a long-sought goal. Achieving it would be a pinnacle of engineering and scientific triumph, and many of today's young nuclear engineers may one day find themselves commissioning the first generation of fusion power plants. Of course, the future of nuclear engineering also faces challenges. Public perception and acceptance of nuclear technology vary widely. Events like Fukushima in 2011 had a chilling effect on nuclear expansion in some countries, as people understandably worry about safety and radioactive fallout. Nuclear engineers in the future will not only need to make reactor systems even safer, but also engage with the public transparently to address concerns. There's a growing movement in engineering for social license, recognizing that technical excellence alone isn't enough. A project must earn the trust of the community. We see this with some of the newer projects. For example, before building the Natrium reactor in Wyoming, TerraPower has been actively holding town halls and discussions with local residents, and incorporating feedback into their plans. Similarly, developers of SMRs in places like Idaho and Tennessee are working closely with communities to ensure their questions are answered. As nuclear engineers, being able to communicate effectively with non-experts, conveying what we do, how risks are managed, and why it matters, will be an increasingly important skill.